Hi everyone. I'll start to present myself. So my name is Ina, and since 2013 I've been a project manager of the small CUBESAT project at Warsaw University of Technology. And this project was developed by Student Space Association, and today I will be speaking about partly about our project in general, and then Krzysiek will be speaking about part of our cooperation, which was made in Scala. So the team, so it's not only me in the project, as you can guess. And here you have the team. Most of people are from Warsaw University of Technology, and we cooperate with other companies and other also people from other universities, but very small. Mostly it's the team of Warsaw University of Technology. And here you have presented some facts about the project. So we started, as I said, 2013, and well, start of the project is start, and end of the project is launch of the satellite. So the launch will be this year, probably summer 2019, on Falcon 9 rocket, as you know, Elon Musk and SpaceX. At the moment, we have around 30 people in the project, and during the whole project, like 5 years, there were around 100 people involved. And we work in 11 teams. Each team is dedicated to most of the team dedicated to the satellite subsystems, and some general teams. Well, this is education part that we also try to relate the project subjects with our diplomas and theses and so on. But what might be interesting for you, that we also wrote a lot of documentation, and this documentation is actually available. And each phase of the project has its own documentation, and each subsystems also has its own documentation. So basically, if you see the website and you go to the website, you can download the documentation and read how to build the satellite. So where we started, it's, as you know, PW-Sat2, so there should be PW-Sat1. So it was the first Polish satellite launched by Viga rocket. It's a European space agency rocket, and it was launched 2012. Now it's not anymore on orbit. It was deorbited after 1.5 years of life. And the main payload was the orbit system. What is the orbit system? I'll tell you a bit later. But it was a very small satellite, as you can see. It was 10 by 10 by 10, and this standard called CubeSat standard is the standard for university satellites and small satellites, and it, let's say, measured by units. So this is 1 unit, and PW-Sat2 is 2 units. So what is the main idea why we build in the satellite? First, it's because we want to learn how to build a satellite to, when we finish our studies, we want to go into the industry and already have this experience how to build the satellites. But it will be too easy just to build a satellite. So we found out that we want to solve some kind of problems. And one of the problems we want to solve is the space debris problem. So if you can imagine that we launch a lot of spacecrafts, rockets, and so on into space. Since you have some numbers here, you can read it, yeah? So it's quite high numbers, big numbers. So if you can imagine that, how many debris we have now on orbit and why it's happening. First of all, for example, if you have a rocket which is launching, then the last stage of the rocket, basically, you separate the satellites from the last stage of the rocket, and then what will happen with the last stage? Well, it will stay in the same orbit and not go back to Earth. Well, Elon did it, yeah. But the last stage stay on orbit. What does it mean? That there's a lot of last stages of the rocket on orbit. There's a lot of satellites which are not working anymore. And what happening? So if you have the object which is not controlled, you cannot do anything with it, then you have a collisions. What do collision? Collision does that you produce more debris. The more collision, more debris, the less place on, in space. So basically, the thing is that if we won't do anything now, if we won't start to solve this problem, in 5-10 years, we won't be able to launch anything into space because it will be just destroyed by the debris. So we wanted to solve this problem, and this is our solution. So we find out that, okay, we have a convention from United Nations that the satellite, after its mission, cannot stay on orbit more than 25 years. So we found out, okay, so we need to develop some kind of system which will deploy at the end of life of the satellite and which will make it deorbit, leave the place to give the place for other satellites. So this, as you can see, this is deorbit sail, because on a, let's say, on a low altitudes, low Earth orbits, up to 700 kilometers, you still have some particles of the air or other particles. So basically, you can produce drag. So basically, as on Earth, by deploying the large structure, structure, you can increase the drag, so you can decrease the speed, so you basically can go down and deorbit, just burn in the atmosphere. So this is the system, which is like 7 centimeters in the diameter, and after deployment, it's 2 by 2 meters, so 4 square meters. So yeah, just a little bit about testing, because SoftwareMill was also helping us with the testing. Because it's really hard to test this kind of system, because it's very mechanical, very automatical, and to properly test it, you need to have microgravity conditions, which is basically really hard to obtain on Earth. So you have many methods, but one of them is just dropping stuff. But it's not dropping stuff from anywhere you want, but you need to drop it in a vacuum. So we went to Bremen in Germany, where they have a drop tower, and we started to drop the sail from, let's say, 8 meters to see how it would deploy. So the guys prepared all the electronics and software for the system for deploying the satellite with the sail. So we could measure and see and record how the sails deployed. This is high-speed cameras. The full deployment, as you saw, it's less than 1 second. Okay, so the main payload is the orbit sail. So basically, if you ask why you build a satellite, just to destroy it. So it might be quite funny, but yeah. But the secondary mission is a sun sensor device. This is a very simple device because it works on light sensors. Why on each side there are 3 light sensors, just for redundancy. And it measures the angle to the sun, basically 2 angles to the sun. This type of sensors, sun sensors, are used in satellites on attitude determination and control systems to help the satellite to know how it's positioned in respect to the sun. And then use the active system to turn it. The accuracy will be around 1 degree. It's not a high accuracy, but since the sensor is very simple and cheap, so this is really nice. And just to compare our accuracy with the reference sun sensor, we bought one commercial one. So another stuff we made by ourselves, it's an electrical power system. So just the power management on board the satellite, and some more mechanical structures, because most of the team is mechanical engineers, the hinges to deploy the solar panels. The rest of electronics, so like 80% of electronics we bought from external suppliers. So here you can see what is inside the satellite. So just going from up, so the sail in the container. We have also 2 cameras they are mainly where to record the moment of sail deployment, but they also can take some pictures of the Earth and send to us. It will be cool. Then we have a sun sensor here, solar panels. These are like shields for protecting from radiation and protecting from the high temperatures. Then we have, two cameras. And electronics, this might be more interesting for you. So we have a radio communication module. This is antennas model based on radioamateur frequencies. Then we have a communication module. Then we have EPS. Sorry. Yeah. Then we have EPS, batteries, attitude control, and determination system. This system is actually a magnetic system, so we have magnetometers and magnetotorquers. So the satellite can turn itself, but it doesn't have any propulsion, so it will not stay on orbit. It just can turn by interacting with the Earth's magnetic field. Then we have onboard computer, and then we have our own board for payload, for experiment. And that's all. And the next movie is how to build a satellite in 10 minutes. But no, it's not 10 minutes. But you can see, because we actually assembled the satellite months ago or 2 months ago. So it took some time. And here you can see how we assembled it with just a part of electronics boards. So we do need in clean room. It's very clean environment. Why you need clean room for building? Because in space you don't have pressure, you don't have gravity. So all the dust is going everywhere. And for example, it can not damage, but let's say cover your optical devices. And also it's not good for electronics to have dust everywhere. So the final stage is, as you can see, the satellite is assembled. And at the moment we are doing the test campaign. So we're doing the vibration testing to check if the satellite can survive launch on Falcon 9. And we're also doing the thermal vacuum testing to see if the satellite is safe for other satellites, for other payloads. So the mission, as I said, will start probably, hopefully, it will be July from the launch of Falcon 9 from California. Then we have commissioning phase, so checking up all the basic subsystems around, few days. Then we have proper, let's say, operational mode, where we test our other experiments, communicate with the satellite, taking pictures, and so on. And then after 40 days, we deploy the sail structure, and then we finish the mission. And then we just need the time to wait to the satellites to deorbit. So it might take around a year. Without this system, it might take like 15 years. So this is the mission animation. So everything what I said in the movie. Deploying the solar panels, and what other interesting things that basically the orbit of the satellite will be 575 kilometers. It will be circular orbit, and after deployment of the sail, the satellite will be going lower and lower, and then there is a possibility to track the satellite with the optical devices. I mean, like with the telescopes or even something less advanced. Hopefully, maybe, it will be visible with the just naked eyes at night. So it will be quite cool to say that, oh, you can see this is my satellite. Few words about cooperation. As you can see, there's a lot of partners involved in the project because as students, we needed money. So we invited a lot of companies to help us. main sponsors are companies, software company and also hardware electronics company. And then we have also a SoftwareMill company, which cooperation will be described by Krzysztof. And then we have other companies, for example, they were delivering us the components or giving us support or providing their services like computing something, giving the licenses and so on. And then, well, I would describe a little bit a problem which we wanted to solve together. So basically, when you have a satellite on orbit, you need to communicate with the satellite. So you need to have a ground station. We have two ground stations. One is a primary ground station, and it's in Warsaw, Warsaw University of Technology. Basically, it's in the center of the city, which is not very good because, first of all, the elevation angle is very high, so because of other buildings in surrounded area. The second thing, because you have a lot of other electronics and radio electronics around, so it's really hard to track the satellite, to communicate with the satellite from the center of the city. So another ground station is in Gliwice at Future Processing Company, and this is our secondary ground station. But the problem is that both of the ground stations are in Poland. Why is the problem? Because if you can see on this animation, well, here you have one ground station, but they are quite close to each other. So this yellow thing is like the visibility of the ground station. So if you can see that it's not many times per day we can communicate with the satellite, and sometimes we will have like few days or even a week without any communication. So it's really hard to know, and we don't have money to actually get another ground stations all over the world. So basically, you need to get the data from your satellite to know whether it's alive or not. So what you usually do with these type of projects, that you engage the radioamateurs community. So there are guys all over the world who really want to communicate with your satellite, like this guy. You can see that he really likes it. So it's really a hobby, it's really fun for the people all over the world to communicate with the satellite. Basically, communicate means, in our case, it's just receiving the data, the telemetry from the satellite. And here you have another example. This is a satellite PW-Sat. It actually died a week ago, but it's from their website. It shows how many telemetry were sent by each radioamateur. So these numbers are the, let's say, the ID of the radioamateurs. So basically, you have a lot of data, and it really works. So a lot of people want to send this data and track your satellite. The type of data they send, because you have basic telemetry, and then you have something more, like pictures or anything else. So I'll pass to Krzysztof.
Hello, my name is Krzysztof Grajek. People call me Chris, because Krzysztof is not really easy for some, especially foreigners. This slide is actually not true. I mean, okay, it is true, but just in a small part, because many people work on that project, on PW-Sat2 from SoftwareMill. I'm just one of them. Cooperation with INA and PW-Sat project started more or less at the beginning of 2015, and I guess it can be described in a single image. We are dancing actually there. I had a full movie, but one of my friends told me not to show it because it breaks all the code of conducts. So as you can see, SoftwareMill is the more happy part actually, I guess, because we write software which is unusual for us. Normally I work on the software which is mainly for financial institutions, credit card companies and all this boring stuff. Whereas with PW-Sat project we can work on completely different stuff. we created since 2015 multiple proof of concepts. Okay, cheers. Multiple proof of concepts projects, and today I will talk only about 3 of them, which made it to GitHub at least, and had some testing and a lifespan longer than a week. First is modem connector. This is actually a library we created out of another POC project we had, where the idea was to actually integrate with the ham radio itself and decode the audio signals we receive from it. But as you can guess, this really turned out to be really difficult. So we found out another project which is called Sound Modem and is really popular among radio amateurs. And we use that to receive APSK modulated data. And then we translated that into AX25 frames, which is like a kind of popular data format for digital transmission using radios. But because requirements really change a lot within that project, and so we couldn't use that anymore. But we left it, it's wrote in Scala. We left it on GitHub, and it's available if you want to use it for receiving digital data from ham radio and plug it into some Scala projects. Okay. The second one, which was shown on Ina's slides, we were used in drop tower tests. This software were used only for like 2 seconds or less. But again, it was a really fun project because people from PW-Sat came to us and asked who will write for us a software which will detect when our satellite is dropped and then release the orbiting sail. And we say, okay, we can do it in Arduino. Who likes Arduino? Everyone likes Arduino, we'll do it. But then, once we started working on that, it turns out that the whole operation has to take less than a second, which became a kind of problem. And we cannot use actually relays like on this image. This is a really first part of development, because the relays are producing sparks, and that's prohibited within the drop tower tests. We cannot use standard capacitors, which are used on Arduino boards. We had to change them for tantal ones. We cannot use standard battery, because for some reason it has to be a special one, etc. That's hardware challenges, and the software challenges as well. We had to, of course, write data to SD card and detect the free fall and do that, all of that within 1 second, and write the statistics from the accelerometer as well to the SD card, and actually flash it just before it will possibly break at the end. So as you can see, projects like that are kind of, have many unexpected things, which is of course fun for programmers and for people who have some hacking abilities. I have some video here. This is actually from my house. It wasn't meant to be ever in a presentation. And I, I played around this module where my kids were watching some kind of movies. Oh, it doesn't work. Well, the module were working. Okay, cannot show you that. Okay, that was 2 really small projects. Right now, we moved our development efforts to ground station application, which again is written in Scala. It's kind of simple application written in Play framework. And the main purpose of it is to gather the data from ham radio enthusiasts all around the world and display it in some nice format, allow downloads of statistics and similar stuff. Maybe I'll show you the real. Where is it? Here we go. Everyone can participate if you know anyone or you are ham radio enthusiast as well and you like tracking satellites, which I heard is really fun. Never did it. And you can upload the audio files here. The guys from PW-Sat2 team will decode it, will filter it and process it through their pipeline. Okay, we gather the digital data from AX25 frames, and this data, it's mostly telemetry data regarding the currents in different parts of the satellite, regarding the temperatures of different MCUs, and all these voltages and whatever the guys at PW-Sat2 team needs. We will be able, but it's not finished yet, we will be able to gather the data from frames to form the images as well, because the satellite is equipped with cameras. The resolution is really poor, but those are modules on the satellite which were visible on Ina's slide. And different modules produce different telemetry stuff. We are able to track the current satellite position. This is a different satellite, but it's working the same way. This satellite is called Atlantis. We are using TLE data to find out the position of the satellite, where it is, how high it is, etc. So the radioamateurs can check where the satellite is at the moment and start tracking it if they are close to it. And that's basically it. Because we are not demodulating the signal ourselves, right now the guys at PW-Sat2 team created a module written in Python, which is part of GNU Radio. And they are sending binary data to our application. We decode it. We find out which part of that binary stream is which telemetry information. We store it and visualize it on the screen. And that's basically it. That was the ground station application is the biggest application we do for PW-Sat team. If there are any ham radio enthusiasts, or if you know any, please recommend the project. And it's available at pw-sat2.softwaremill.com, where you can log in using like third-party providers, Facebook, Twitter, Google, etc., and upload your data. Once the satellite, of course, will launch in July, hopefully. And that's basically it. Thank you very much.